Okay, so third lecture. So in this lecture, the main point, the main point for the beginning of the lecture is about existence theory. Because I mentioned at the beginning of the first lecture some examples of minimal hypersurfaces, minimal surfaces, but for the moment we don't know how to construct them. And we don't have so many examples to play with and test the theory. So existence theory. And in fact, it's existence theory 1. And tomorrow I will do the second part of the existence theory. Okay. So I don't remember the number. And so the question is, okay, as I mentioned, minimal surfaces are critical point of the area functional. So you want to construct critical point of a functional. So the basic idea is, okay, I will do this by minimization. I want to take some class of surface and find inside this class of surface one which has minimum area. And it gives me a critical point of this. So this idea is at the origin of a celebrated problem, which is the plateau problem. And it's plateau problem 1. So, and the question is the following. So you look at R3. And the basic question is the following. So you look at a curve, a Jordan curve, inside R3. And you want to find a surface which is minimal. So a priori just a critical point of the area functional with boundary exactly that curve. And the idea, okay, I'll look to a critical point, so let's look to a minimum of this area functional. Okay, so how can I do that? So the basic idea is to select a class of surface with boundary exactly this curve and try to do minimization of the area among that class. So basic class, if here it's a Jordan curve, is to take the unit disk and look at all the maps phi from the unit disk to R3. So this is included in R3, such that phi of S1 is precisely a parametrization of gamma, where gamma is this curve. And the idea is, okay, let's look to the following problem. The infimum of the area of the image of the disk by phi among all that phi in the class. And try to prove that there exists a phi that gives you a minimum for this problem. And if you have one, okay, but then it's a minimum for the problem, so it's a critical point, and the surface you get, this disk, is a minimal surface. So a priori, I won't give any idea of the proof of the theorem, but let me mention the main problem to this question is the following. You look, in some sense, it's the same idea as, okay, I want to find a geodesic from one point to another one. I look to all the curves between these two, and I look at the minimum, and this minimum is realized by a geodesic. Okay? The difference with the geodesic case is the following. Look at the boundary, which is just a planar circle like this. So the solution, of course, is just the disk in there. But think about a minimizing sequence. So minimizing sequence for that case, it could be, okay, it's something which is very close from the flat disk like this. And you look at the minimization of the area. But one thing that I can do to this disk there is to add some air with a very, very small area like this. And I can put a large number of these things everywhere on the disk. But it's still a minimizing sequence because the amount of area you put there is very, very tiny. Okay. So what you see is that if I take phi to parameterize this disk with these long curves there, you get something which is still area minimizing, but you can't expect to have any minimization, any limit for that sequence phi of minimizing for this minimizing sequence. If you want to prove some compactness issue, you want to take care about this, and you have a big trouble. So this problem was solved by Douglas and Rado. So in the 30s. And the idea, the basic idea is, okay, you look at the area, it's not the good functional to look at. And the good functional to look at is the Dirichlet energy of phi, which is just 1/2 the integral of what I denote of the differential of phi square. And the thing is that if the parametrization there is conformal, then the area and this quantity are almost the same. You just have to put to the square. And you get exactly the same quantity. So minimizing for this or this, it's the same problem. The thing is that that kind of surface for this energy, the energy is very large. The energy of this is very large, even if the area is very close to be the minimum. So minimizing for this, it's a better problem to look at. Okay, I won't say more about the proof of this of the following result, which is so due to Douglas and Rado. So theorem, Douglas and Rado, which say, okay, so you take gamma, a piecewise C1 curve, a closed curve in R3. Then there exists a map U from the disk to R3 such that, so first you have some regularity issue for U. So U is a continuous function on the closed disk, and it's in some Sobolev spaces on the disk. And in some sense, this is exactly the space you want in order to define this Dirichlet energy. Okay, the thing that you know is that on the boundary of D, you have a parametrization of the curve gamma, so it's monotone. And surjective. So the map U gives you a parametrization of the curve gamma. The third property is that, in fact, U is smooth in D. And the last property, which is what you want, is that the image of U minimizes the area among all such maps. Okay, so among all these maps, if you look to the area, the U you obtained by this theorem gives you the minimum of the area. So you get the image of U is a minimal surface inside R3. Okay, so let me mention some points. First, what is not known by this theorem. After there is some work and you get more information about this. First, you don't know that U is in fact an immersion. Maybe the differential of U vanishes at some points, and so you have some trouble there. The surface could have some ramification point, something like that. You don't know anything about the fact that the surface is embedded or not. It depends on gamma, in fact, to have some result in that direction. And moreover, maybe there is other surfaces with boundary gamma, but with less area. The thing is that here we fix the topology of the surface, we want a disk. Maybe it's not the good thing to look at, maybe the good topology is a torus minus a disk, something like that. Okay, but this is the first result in the existence theory, the general existence theory for minimal surfaces. And let me also mention that in a Riemannian manifold, there is a similar result which is due to Moret in that case. There is also another question which is not always very, very clear about this, is what is the regularity of U at the boundary? Here I just put continuous, but yes?
Is that means that leaving the immersibility properties doesn't allow us to get down to the area?
No. It depends exactly what you want. If you fix the topology, and the fact is that what you prove is that in fact the point where the surface is not immersed are isolated, because what you have behind this, the coordinate function of U are harmonic on the not on the unit disk. It depends if you choose a conformal parametrization, it's harmonic, so the points are isolated, and we know how are the singularities at that point. So it's not a strange non-immersion case. It's just you know exactly how it's not immersed. Okay, so this is the first result in that direction, and in fact Douglas earned the Fields Medal for this result, and some other in that direction. So let me speak now about what I call Plateau problem 2. In fact, the name Plateau comes from a physicist named Plato, who was first the one to ask the question of the existence of such a minimal disk. So what I want to speak now is what I call Plateau problem 2. So okay, here we have a disk, so we have minimal surfaces with boundary. So what about minimal surfaces without any boundary? So we still have in mind the idea, okay, I want to do the minimization procedure to find some critical points of my area functional. So what we know is that in R3 there is no compact minimal surface without any boundary. So a priori it's hard to do minimization in that case. So forget about the case of R3 and think more about a compact. So M, a compact 3 manifold. And look at a closed surface inside this compact 3 manifold. And what you want to do is to try to minimize the area in some class of closed surface inside this manifold. So the thing is that, okay, if you take, for example, a ball inside the manifold and you assume that that ball bound that sphere in the manifold, and assume that this sphere bounds a ball. So the thing is that the sphere, you can shrink it into the ball and all the area in some sense disappear and you see nothing. So what you see is that a priori, if you want to be sure that a minimization procedure will give you something which is not zero, you have to assume something about the fact that you can't compress the surface to a point in some sense. So in some, the idea is that you have to assume some hypothesis on the topology of the surface inside your ambient manifold. And if you do such an assumption, which is in some sense the fact that the surface is non-trivial for some topology inside the ambient manifold, then you can do a procedure of minimization that will produce a minimal surface. And in fact, this work has been done by several persons. You have several approaches, several notions of topology is non-trivial, is not trivial. So let me mention several persons. So there is, in some sense, a first work which is due to Sachs and Uhlenbeck. And what they do is assume that you have assume that the pi 2 of M is non-trivial. So take a non-trivial sphere inside this free manifold and do the minimization in the homotopy class of this sphere. And the thing is that they prove that you can do this, and at the end you find minimal spheres that realize the minimum. I don't want to enter into the details of the result, but you can do this. In some sense, in the same direction, there is a work by Shen and Yao. And so in these two cases, the minimization is in the homotopy class of the surface. So you obtain something in that direction. And then after, there was a result by Mix, Shen and Yao. Where they say, remove, don't look at homotopy class, but look at isotopy class. It's not exactly the same. And the advantage to this also is that, when you look at homotopy class, maybe you leave the fact that your surface is embedded. A priori, it's not clear at all that the minimum would be embedded or not. If you look at isotopy class and you start from the isotopy class of an embedded surface, so you can expect that at the end what you get is an embedded surface. And so there is a result, and I will mention not exactly the version that appear in the paper by Mix, Shen and Yao, but the one that appear in a paper by Haas and Scott. So let me state the theorem. So you take M, be a closed free manifold, which contains an essential sphere. So a sphere that do not bound a ball. And the idea, let's try to do the minimization in the isotopy class of this sphere to produce a sphere which has a minimum area among all spheres which are essential in the in M. So so what is the definition? So you let F be the collection of essential spheres and you define I to be the infimum of the area of S for any S in F. And what you want is to prove that there exists a sphere, an essential sphere, so S in F, such that the area of S is exactly I. So the theorem tells that then there is a sigma in F such that the area of sigma is precisely equal to I. Okay, it seems like it's the ideal theorem you can expect in this problem, but in fact it's not exactly this that you get. In fact, you have two cases. So either you get exactly this. So you have exactly a sphere, an essential sphere with area is the least area of among all the areas of essential spheres, or there is an immersed, an embedded RP2 P in M with area. So of course P in M, P is minimal. The area of P is 1/2 this number. Of course, yeah, let me mention something. This quantity is positive. No, sorry, it's not an assumption, it's a conclusion of the theorem. So let me add something there. So first, I is positive and it's realized either by a sphere or by twice RP2. And in fact, what is the link between this P and all the spheres that appear in F is the thing that with the boundary of a tubular neighborhood of P is inside F. So you look at the boundary of a tubular neighborhood of that P, it's a sphere, it's essential, and in fact you have exactly this. Okay, so this is the version when M is a closed three manifold. In fact, you can do exactly the same if M is compact with boundary. You have the same. But with an extra hypothesis. What is this extra hypothesis? Is the fact, okay, when you want to prove this, what you do is you select a minimizing sequence and you try to prove that you have a limit. And you want to control what happens when you do this. And the thing that you want to be sure in this procedure, when you have some boundary somewhere on M, is that you don't try to escape the manifold across the boundary. So you have to put an hypothesis on the boundary in order to be sure that you don't escape the manifold. And this hypothesis is the following one. What's called the boundary of M is mean convex. And what is this? It's just the fact that the mean curvature vector along of the boundary of M points into M. So the boundary of M is like this, and M is there, and it's not like this. So if you think about the case of a geodesic, and you have a surface with boundary, in order to be sure that the geodesic lies inside the surface, you assume that the boundary is convex, and if you are in this situation, the geodesic wants to escape the surface, and you don't want this. So it's exactly the same. You put this hypothesis, some mean convexity of the boundary, and you get the same result. Yes?
If the minimum is attained by a sphere,
yeah.
this sphere
Yes, of course. Yeah, because if you try to deform it, you don't escape this collection of sphere. It's still a sphere and still incompressible, essential. And so you have a critical point. So the area of the original one is smaller than any other one in the deformation. So you do the computation. What you get is a critical point of the area functional, and it's a minimal surface because we have computed the Euler-Lagrange equation of this at the first lecture, and exactly h is equal to 0. So the idea is, okay, I want a critical point, I do minimization, and I find a minimum, so it's a critical point. Okay. Okay, so let me mention another result, more or less the same, but okay, sometimes you don't have a sphere, and you want to work with other surface than a sphere, you want to work with something else, and you have exactly the same type of result. So it's basically the same result, but for other topology. So you let M be. So there is a topological assumption in order to be sure that what happened in the first theorem does not occur there. So you assume it's RP2 irreducible. So closed. Riemannian three manifold. And F okay, so sigma be an incompressible surface. So I recall that this means that the injection of sigma inside M is pi1 injective. The pi1 of sigma is inject into the pi1 of M in this hypothesis. RP2 irreducible, it's a topological hypothesis in order to prevent what happened in the first theorem to occur. So the thing is that any sphere bound is not essential, and there is no embedded RP2 inside the manifold. So in some sense, it tells you, okay, if you try to do the first theorem, in fact, if you try to prove this theorem, which I will mention, in some sense, maybe what can occur is that at the end you get a surface, but maybe plus some extra spheres that appear. But this hypothesis tells you, okay, there is no extra spheres in the theorem. Okay, so incompressible surface embedded in M, and you let F, as before, be the collection, be the set of all surfaces isotopic to sigma, and I is the infimum of the area of S for S inside F. So first I is positive. Sorry?
Before you go to F, the set of all
Yeah.
incompressible surfaces.
Yeah, and before it was all the essential spheres. Here it's just the set of all surfaces isotopic to sigma. It's not the space of all incompressible surface, for example. Here, in some sense, I fix the genus and I fix the way it is inside the ambient manifold.
And before you can ask in the subclass of the incompressible sphere isotopic to that one.
No, it was not all the. The thing is that maybe if you have a sphere that bounds something which is not a ball, maybe when you do the minimization, try to do this in the isotopy class. Maybe what could happen is the following thing. So you start with a sphere that bounds something, which is not the ball. And you try to minimize the area of this. So maybe what happens is that, okay, what you will see something in the minimization procedure like this. So you have a sphere close to a new sphere there, and a long collar between them. And here you have something which is not a ball. Here you have something which is not a ball. So maybe at the end you get, in some sense, this plus this. And so it's not exactly the same thing. So that's why you want to minimize among all essential spheres to be sure that even if this produce, this one or this one is not essential. So it has to disappear, in fact. Here you don't have this problem because you have a control on the pi 1. Okay, so you have this, so I is positive, and I is realized either by S in F or I over 2, so either I is realized by S in F or I over 2 is realized by some P whose boundary of the tubular neighborhood is inside F. Okay, it's exactly the same picture. Maybe the surface fall into itself and disappear. But let me mention something. We produce all these surfaces by minimization. So they are critical point of the area functional. But in fact, they are also stable surfaces, stable minimal surfaces because they are minimum. And so the question is, okay, now let's try to do something and in some sense apply some idea of this morning to say something about these surfaces that we construct like this. And that's what I want to study now is the following question is to understand, so area minimizing surfaces but as in this morning I need some extra hypothesis to say something really interesting. And as this morning, what I want to put on as an hypothesis is a lower bound for the scalar curvature. Okay. Okay. So let me make an example to begin. You look at the three torus, T3. So it's clear that inside these three torus, you have a T2, two torus. You can see it, for example, like this. So let me draw a picture of the three torus. So you glue the opposite faces. And you can think about this T2 like this, inside it. Okay. So it's clearly incompressible. The pi 1 inject into the pi 1 of the ambient manifold. So you can apply this result to produce, in the isotopy class of this torus, a minimal guy. So here I do not say something, but I put any metric, Riemannian metric on the three torus, not the Euclidean one. A priori, not the Euclidean one. So I have somewhere inside it a two torus which is area minimizing among all the three torus isotopic, among all the two torus isotopic to this one. And the question is, okay, I want to understand something about the geometry of this two tori and say something about maybe the ambient manifold. Okay. Okay. So in order to look at this example, let me generalize a bit the question. So let M be a three manifold, a closed, or not necessarily closed, a three manifold. Okay, and you look at and you assume that the scalar curvature is larger than some constant R0. And you consider inside it sigma be a stable minimal surface inside it. Okay. So let's do a computation that we have almost already done this morning. So you apply the stability equation of this morning with the constant function equal to 1. So you have 0, which is larger than minus the Ricci curvature of the ambient manifold in the normal direction plus a square on sigma, which is non-negative. Okay. And we do exactly as in this morning, the same computation on this term and this one. So let me redo this in order to recall everything. So the thing is that the Ricci here we can add the sectional curvature of the ambient manifold on the tangent space to sigma. You remove it at the same time.
And we master this into closed?
Yes, closed. Sorry. Stable minimal surface, closed. Yes. Okay, so you do this, and as in this morning, this term can be written as, and maybe, no, I won't use this now, or maybe I will keep this. So this term A, I will put this as k1 square plus k2 square plus 1/2 of A. So I consider k1 and k2 the two principal curvatures of my surface. So here it's minimal, so k1 is equal to minus k2, but in the following I will use some constant mean curvature surface, so this will not be the same. But maybe I will, if I succeed, I will keep this computation there. So okay. So as in this morning, the sum of these two terms is 1/2 the scalar curvature of the ambient manifold. So if I want to be take care, it's R bar there. Okay. Minus this term. And this one is just what? It's just plus 1/2. So k1 plus k2 square plus k1 k2. That's right. Minus k1 k2. Yes, minus k1, k2, it's better. Plus 1/2 a square. Okay. So finally, I get the integral over sigma of minus 1/2 r bar. There is plus twice the scalar, the mean curvature square. So k1 plus k2 is twice the mean curvature. Here, these two terms by Gauss equation gives me minus the sectional curvature of my surface sigma plus 1/2 a square. Okay. And maybe I can put this on top. Okay, but now I put the hypothesis, the fact that r bar is larger than r naught. So I get that the integral, so something is non-negative, so it's integral minus. So it's minus 1/2 of r naught plus 1/2 of r naught minus r bar. Okay, plus. So I use the fact that here the surface is minimal, so I have the curvature of the surface minus 1/2 a square. Okay? And I use the fact that this quantity is non-positive. So it's less than, so what I get is minus 1/2 r naught times the area of sigma. This term is also non-negative. I get this term, and by Gauss-Bonnet, this is just 2 pi times the Euler characteristic of sigma. So I get an inequality between the topology of the surface, its area, and the constant r naught. Okay, so what I have proved is the following. So it's the proposition. So with the above hypothesis, I get, so r naught times the area of sigma is less than 4 pi times the Euler characteristic of sigma. With equality, if and only if, what? So if I have equality there, I must have equality there. So it implies that, okay, A has to be 0, this has to be 0. So sigma is totally geodesic. The scalar curvature is equal to r naught along sigma. And moreover, if I go back to the beginning of the statement, so in this inequality there, the first one, A is equal to 0. So Ricci, the integral of Ricci has to be positive, has to be negative. Okay, but sorry, it's not this. No, sorry. Let me say something. If I have equality, I have equality in the first inequality. So it tells me that the constant function 1 is in the kernel of the operator. So it tells me that, okay, Laplacian of 1, which is equal to 0, plus Ricci times 1 plus A squared times 1, so A squared times 1 is equal to 0, is equal to 0. So Ricci is equal to 0 along sigma. So Ricci bar of n is equal to 0 along sigma. And because of this, You have also, you can extract another inequality somewhere. So where it is exactly, so which is equal to 0. Let me say where it is. Okay, I don't see exactly where it is, but what you get, oh yes, which is equal to 0. Yes, which is equal to 0. The scalar curvature is equal to R0. So the sectional curvature of the tangent space, the sectional curvature of the ambient space along the tangent space to sigma is equal to R0. Since the surface is totally geodesic, it tells you, okay, the sectional curvature of the surface is equal to R0. So moreover, you have K of sigma is equal to R0. So you have proved that if you have equality in the inequality, then your surface, for example, is totally geodesic. It has constant sectional curvature. So it's really a well identified surface inside this. You have the Ricci curvature is equal to 0. You know a lot of things, in some sense, at order 1 or 2 in the neighborhood of the surface sigma. And in some sense, if you look to this, what you see is that the ambient manifold splits close to at order 2 along sigma. You have, in some sense, an infinitesimal splitting of the manifold. And the question is, okay, is it possible to prove that you have, in fact, a global splitting of the ambient manifold? But before looking at this, let me make some remark. So first, what is this? So it tells you, for example, that if R0 is positive, so this quantity is positive, so it tells you that the Euler characteristic is positive, so the surface is a sphere. So sigma is diffeomorphic to S2. And in fact, what you get is just that the area of sigma is controlled by 8 pi over R0. So what you get is an upper bound for the area of sigma. Okay, if R0 is just non-negative, what you get is that this Euler characteristic is non-negative, so sigma is either S2 or the 2 torus. Okay, and if R0 is negative, what you get is that, okay, sigma has an area which is larger than 4 pi over R0 times the Euler characteristic. Sorry. So larger than, which is just 8 pi over R0 G minus 1. So let me recall that R0 is negative. So, sorry?
The R0 is negative.
1 minus G.
Sorry. Yes, 1 minus G. Yeah, of course. Okay. So the thing is that R0 is negative there. So in order to have something which is interesting there, you want to have a lower bound on the area. So you look only to the case where the genus is at least 2. So what you get is a lower bound for the area of a minimal surface inside your ambient manifold, when it is stable, of course. So it's not really so strange, in fact, but you pass from an upper bound to a lower bound in the same problem, a priori. Okay, so what is the theorem I want to prove now? Is the following result. So my idea is, okay, assume that you have equality in the inequality and try to prove that you have a splitting. So theorem. So same hypothesis as before. So M 3 manifold closed, not so closed, manifold. The scalar curvature is larger than R naught. And sigma, what is sigma? So before it was a stable minimal surface inside M. But here I will remove, I will change. It's not stability I want to assume, it's more than this. So it's a closed area minimizing orientable surface in M. And here I put area minimizing, so I have to take care about what is the class among which you are area minimizing. So it's area minimizing in the homotopy class. You will see in the proof that any reasonable class will work in this theorem, in fact. But in some sense, the thing is that here I do not assume anything about the fact that sigma is embedded or not. So that's why I need to be really precise about the fact that it's the homotopy class I consider there. So if you have equality in the inequality, so 4 pi times the Euler characteristic, then M split, say M is a quotient of sigma times R. Yes, that's okay. So, and recall that we already know that sigma is a surface with constant sectional curvature. So we have a splitting theorem like this. Okay. So I do not mention who is the author of this result because in fact it's a result made by several authors. So the first case was studied by Kai and Galloway. And it's the case where the genus of the surface is equal to 1. So here it's equal to 0. And R naught is equal to 0. Okay. The second version of this result is due to Bray, Brendel, and Neves. And it's the case of the genus is equal to 1. 0, sorry. The case of the sphere, and it corresponds to the case where R naught is positive. Then after the case where the R naught is negative and the genus is larger than 2 is due to Nunes. And in fact, more or less at the same time, the proof of this guy, this guy gives the proof of this when G is larger than 2. There was another version which is due to Mikalev and Moraru, which in some sense give a unified proof of all this for all G. And this proof, and I will more or less follow this proof, is based for a big part on ideas that appear in this paper by Bray, Brendel, and Neves. Okay. But before giving the proof of this, let me make some remark. Okay, remark. The case of the genus 1. So look at the picture I made above. Assume that on these three towers you put a Riemannian metric with positive, non-negative scalar curvature. So you can produce an area minimizing torus there. So because R0 in that case is 0, the Euler characteristic is 0, so you have equality there. So this result tells you, okay, you have a splitting. And the splitting is just the fact that you have the surface is a quotient of a flat two torus, in that case, with R. So it tells you, okay, in fact, this the metric with a non-negative scalar curvature is in fact flat. So what you have proved there is that it's impossible to put a metric with a non-negative scalar curvature on a 3 torus except the Euclidean one. And in some sense, it's a baby case for positive mass theorems, things like that. But it's the proof you will see is not so difficult to obtain. Okay. It's not so difficult if you assume the fact that you can put area minimizing torus inside this. Okay. So G equals 1 implies that on phi3 there is no metric with R bar larger than 0 except the Euclidean one. So okay, so let's start the proof of this. So what is the ID? The ID is, okay, let me make another remark which is important. Is it possible to prove the same result but not by putting area minimizing there, but stable surface? The answer is no. And why it's no? Because of the following thing. You take a sphere, but you put on it, so 3 spheres, but you put on it a metric like this one, such this S2 is totally geodesic, okay? You do this by symmetry. And you assume, moreover, that the Ricci curvature in the normal direction there is equal to 0. So you can do this really easily. You put a metric and you flatten it close to the equator. So it implies that this sphere there is in fact stable. And you can do this also by assuming that the scalar curvature is strictly positive. Because you have another contribution to the scalar curvature except Ricci, which is the sectional curvature of this sphere, which could be chosen to be equal to 1. So there is no problem to this. So what you see, and of course it's clear that this S2 is not area minimizing because you can push it and make it disappear at the pole. So you have to assume something stronger than just stability. Okay. Okay. So what is the ID, the basic idea of the proof? Is okay, let's try to construct, using this hypothesis, another surface in the homotopy class of sigma with less area and find a contradiction, or if you don't have a contradiction, then you have to split like this. This is basically the idea. So the thing is that you start, so let phi from sigma to R, sigma cross R to M, and you take a point P in sigma, a parameter T, and you look at the point at distance T in the normal direction to P to sigma. So you look at the Fermi coordinates on the neighborhood of sigma. In fact, you look at the global Fermi coordinates on M. So the idea is to prove that in fact phi is an immersion, a global immersion for any R, for the whole R, and a local isometry. So if you have this, then the theorem is proved. You know that you have a cover of M, which is given by sigma cross R. Okay. So let's try to apply the idea, okay, find another surface in the homotopy class of sigma with less area. So basically the idea, okay, you look at the equidistant surface and try to compute the area of this and see, okay, the area of this is smaller, so except if I have some particular things in the problem. But the thing is, does not work like this, and this is the idea introduced by Brendel and Neves. So the idea is the following thing. So it's given by the proposition which is there. So there is delta positive and W, a function from sigma times minus delta to R, such that. So first you assume that, and I will explain after what all of this means. If you take a point P in sigma and you take the parameter 0 there, then W is equal to 0. You assume that the derivative with respect to the real parameter here of W at P0 is equal to 1. Okay. You assume that the integral of W Ps minus S is equal to 0 on sigma. And moreover, you assume that sigma sub S, which is just the set, yes, this a priori is not an immersion in the whole space, but you assume that it's, you can be sure that it's an immersion on sigma times minus epsilon epsilon, okay? And you lift the metric on M to sigma times minus epsilon epsilon, and you work only on sigma times minus epsilon epsilon. It's in some sense a copy of a piece of M, and you can work on this. So you look at the set of points P, W, Ps in sigma times minus epsilon epsilon, P on sigma. So what you assume on sigma sub S is that sigma sub S has constant mean curvature. Okay. So what is the idea? The picture is the following. So you have some sigma. So here you have sigma, and here you have, in some sense, epsilon, here minus epsilon. And what I said before, the basic idea is you look at the equidistant surface to sigma, so you look at this, and you try to compute the area of this and find something. But it does not work like this. The idea is, okay, you look at the graph of the function W, you fix on some S, and you look at the graph of the function WPS. So what you look is to sigma sub S, which is some surface there. So here it's sigma sub S. So the thing is that sigma naught is just sigma because of this hypothesis. And so you look at this. Okay. So it's not the equidistant surface because, yes?
So the sigma depends on the epsilon, or where does it come from, the epsilon?
Delta depends on epsilon.
Delta, okay.
Okay. You have some delta,
Okay.
which is sufficiently small such that W is less than epsilon for any P and for any P and S. Everything lies in this tubular neighborhood of sigma.
Okay, so it has to be for any epsilon there is a delta.
Yes, but okay. For any, yeah, the thing is that you fix epsilon positive, such that phi from sigma cross minus epsilon epsilon is an immersion. I fix epsilon before the proposition. Okay. So as I said, sigma sub s is not the equidistant surface to sigma. But the thing is that we put this hypothesis. The mean value of W is S. So in some sense, it's almost the equidistance at distance S to sigma. Okay, so here it's just an hypothesis to say, okay, you do really something, you move away from the surface and you move away with constant speed 1. And the thing is that you choose this in order to have this hypothesis, constant mean curvature. Okay. So the proof of this is just implicit function theorem. You have to choose the space, but it's just implicit function theorem. You can do this. Okay. Okay. So where is the following? Okay. So in order to fix some notation, I will denote by G of P of S the point P W. What is the notation I use? PS. So this is just a parametrization when S is fixed of the surface sigma sub S. Okay. And I will also use the following notation. So nu n of S, n sub S, is the unit normal vector to sigma sub S. Okay. And you define rho sub S is just the scalar product of n sub S with the derivative of G with respect to S. So what is this? This is the way you deform the surface sigma sub S at time S. Okay? This is the normal to this surface sigma sub S. So rho sub S is just the contribution in the normal direction to the deformation. Okay. Okay. So let us have a look to H of S, the mean curvature of the surface, sigma sub S. So this is a constant because I assume the mean curvature is constant, so it does not depend on P. And I look to the derivative of this with respect to the time S. Okay? And I apply the formula of this morning that tells me how you can compute the derivative of this when you have some deformation. So what is the answer to this? It's the Laplacian, so sub S, so with respect to the metric on sigma sub S of the function rho S, plus the Ricci curvature of the ambient space in the normal direction, plus the square norm of the shape operator of sigma sub S times rho S. And there is an extra term which is the derivative of the mean curvature in the tangential direction to the sigma sub S. But here I assume that the sectional curvature, the mean curvature is constant along sigma sub S. So this derivative is just 0. Okay, so I have this. Okay, so let's do still the same computation as before, as I've done there. In order to transform still the same term, which is there and there. You can do exactly the same. So what you get at the end is the following things. It's this. So you divide everything by rho s. So you get that twice h prime of s over 1 over rho s is equal to this over rho s plus this term. And you do the same algebra in order to make appear everything. And so what you get at the end is this expression. So you have 1/2 r minus the sectional curvature of sigma sub s plus twice h of s square plus 1 over 2 the norm of as square. So here I have this mean curvature that appears because it's not equal to 0 for the moment. I don't know. Maybe, but for the moment there is something. So I have this term there. And you use the fact that r bar is larger than r naught. So you have this. Plus 1 over r naught minus k sigma sub s plus 1/2 r bar minus r naught plus twice hs square plus 1/2 as square. Okay, so you have this. Okay. Okay, so you have this and you integrate this quantity. So first, as I said, h is constant, so it gets out from the integral, but you have this term that appears, and so it's on sigma sub s. And what you get, because of the inequality, the fact that r bar is larger than r naught, this quantity is non-negative, this quantity is non-negative, all of this, what you get is just, so this quantity is larger than the Laplacian of s rho s divided by rho s plus 1/2 r naught times the Euler characteristic times this, the area of sigma sub s minus the integral of the sectional curvature of sigma sub s on sigma sub s. Okay. Oh, let me make a computation. You can integrate this by part, and what you get is just the gradient of rho s square divided by rho s square. Oh, one remark I do not make. For s equal to 0, these two vectors are the same. So rho s is equal to 1. So you can assume that rho s is not equal to 0 in the problem. So that's why I can divide by rho s there and before. So plus 1/2 r naught, the area of sigma s, minus 2 pi times the Euler characteristic of sigma s. Okay, but the Euler characteristic there does not depend on s, so it's just the same as a sigma naught. And this quantity can be computed by the area of sigma naught, in fact. This is the hypothesis. I have equality in the inequality. So what I see at the end is that this quantity, so this is non-negative, so plus r naught over 2 times this minus the area of this. Okay. So I have this inequality. So here there is two cases to study, and since I don't have time to look at all the cases, let me do the simplest one. So assume that we are in the case where R0 is non-negative. Okay. So I use the fact that sigma naught is area minimizing. So this quantity is non-negative. This is non-negative, so everything is non-negative. So this implies, because I use area minimizing, I get that H prime of S is non-negative. Okay. So H of S, H of 0 is the mean curvature of sigma naught. Sigma naught is minimal, so H of 0 is equal to 0. So I get that the mean curvature is non-negative. But in which sense points the mean curvature there? So the picture of before was like this. Here I have my surface sigma sub S, sigma naught. And in fact, the mean curvature point is like this. It's HS and S. The choice I made for NS is this one. So the mean curvature vector is this one. So it tells me that when I move in this direction, the derivative of the area of sigma sub S is equal to H of S minus twice H of S rho S sigma sub S. So this quantity is non-negative, this quantity is non-negative, there is a minus 2, so this is decreasing. So the area here is decreasing, but you are area minimizing, you have a problem somewhere. So it tells you that in your long inequality there, you have equality everywhere. And so you get equality everywhere. So, I don't know exactly what I can remove there. So equality everywhere. So I won't finish exactly the proof, but let me say a few points that you can recover from this. Okay, so you have equality everywhere, so sigma sub S in area is equal to sigma naught. So sigma sub S is area minimizing. It's in the same homotopy class, it's just you push a bit the sigma naught. It has the same area, so it's also area minimizing. So H of S, which is the mean curvature, is equal to 0. And you can apply, and you have also equality in the inequality for stable surface in that case. So it tells you, okay, A of S is equal to 0. So in fact, it's also totally geodesic surfaces. It tells you, okay, Ricci of N of S is equal to 0. You get also something which is the sectional curvature of sigma sub S is equal to R0. One thing that you get also because of the equality everywhere is that here this term has to vanish. So rho S has to be constant. along sigma sub s. Okay. So believe me, you put this together and you prove that you have the splitting. And maybe it's very close from the argument of your talk. Once you know all of this, it's more or less like you have a distance function and you have a splitting with this. So this finished the proof of the result. Yes?
You continue with sigma delta over 2.
Yeah, the thing is that, okay, what I have proved is the following. I have a local splitting of the manifold. So it tells me, okay, in some sense, my function, I erase this, but the map psi, I believe it was psi, from sigma cross R to M, what I want to prove is this is an immersion with this, and it's an isometry. This theorem, this result tells me, okay, there is an epsilon such that this is an isometry, local isometry from from sigma times minus epsilon epsilon. So the set of T where it is a local isometry is an open subset. It's easy to see that it's a closed subset by connectedness. You get R, and this finishes the proof. Okay? So let me mention something. Yeah.
M is not compact.
No, M could be compact. I look at the cover. I say M is a quotient of sigma times R.
My hypothesis is not compact.
No, I do not assume anything. It could be compact.
Could be compact?
Yes, you can think about the torus. Everything applied to the three torus. The thing is that the three torus is a quotient of the product of the two torus with R. Okay, it's just this. So of course, here I made some assumption. I assume that R naught is non-negative. And the thing is that, okay, if you assume that R naught is negative there, so here you have a sign, here you have a sign, but this tells you, okay, this quantity is negative. So you don't get anything about h prime of S, it's not on the right way. So in some sense, you have to be a bit more clever in order to understand that all this, in some sense, ODE gives you that in fact h of S is really what you get at the end is this, at least on a short interval. And you apply this in the short interval, it's exactly what you want to prove. It's a local splitting theorem that extends to the whole manifold. Okay? Okay, so I think I will stop there. Thank you.